So, I want you to look at a clock right now. Just watch the secondhand tick.
Yeah, that relentless march forward.
Right. But what if I told you that every single second ticking by isn't actually time moving forward? Like, what if it's just the agonizing one-way measurement of your own biological machinery breaking down?
It's a dark thought, but mathematically it's highly accurate.
It really is. Today, we have this massive stack of mind-bending sources sitting on the table. We're pulling from quantum physics breakthroughs in science news and scientific reports.
Plus the philosophical treatises of Tenzin Trep.
Exactly. And some truly provocative insights from the Still Science Lab. So the mission for this deep dive is to basically completely dismantle and then rebuild your understanding of time.
Because when you really look at the fundamental mathematics of the universe, that river of time you feel sweeping you into the future, well, it doesn't actually exist.
Okay, I have to push back immediately on that because I am sitting here right now experiencing reality as a strictly one-way street.
Right, of course you are. We all are.
So if time doesn't exist as this fundamental directional force, why am I getting older? I mean, why is it that if I drop my coffee mug right now and it shatters on the floor?
It never miraculously reassembles itself and jumps back into your hand.
Yeah, exactly.
So the shattered mug is actually the perfect way to understand this. We really need to separate the concept of time from the concept of entropy.
Entropy being like disorder.
Yeah, the second law of thermodynamics.
Why?
It dictates that in any isolated system, disorder or entropy always tends to increase.
Because there are just way more ways for a mug to be broken than to be perfectly put together.
Precisely. So as your body or the mug or the entire world around you moves from this state of high order to a state of disorder, we perceive that localized structural decay as the arrow of time.
Wow. Okay.
But that arrow isn't baked into the bedrock laws of motion. A subatomic collision plays out with perfect mathematical legality, whether you run the tape forward or backward.
Wait, really? The math works exactly the same in reverse.
It does. There's absolutely no fundamental current pushing things in one direction at the quantum level. It's purely a statistical reality of complex, macroscopic systems breaking down.
So we aren't passengers on this, like, cosmic train moving toward a destination called the future.
Not at all.
We're literally just highly complex biological machines slowly falling apart, and our brains just interpret that ongoing decay as time passing.
That is the incredibly uncomfortable truth of macroscopic physics, yes. What you and I feel as time is strictly a symptom of entropy.
Yeah, that's rough. But okay, if our everyday experience of time is just this localized illusion dictated by entropy, it makes me wonder what happens when we zoom in.
To the quantum scale.
Right. If we go down to the quantum level where physicists can actually, actively manipulate entropy and isolate particles from their chaotic environment, could we actually make time run backward?
Well, yes, we can. And researchers already have.
See, that blows my mind.
The results we're seeing in recent experiments completely upend all our standard classical assumptions about reality.
Let's talk about that study led by physicist Roberto Serra, because the mechanics of what they did are just wild. They took chloroform molecules,
which consist of carbon, hydrogen, and chlorine atoms.
Right. And they manipulated them in this highly controlled environment. Specifically, they used nuclear magnetic resonance to make the hydrogen nucleus hotter than the carbon nucleus.
And under standard macroscopic conditions, we know exactly how that scenario ends.
The hot stuff cools down and the cold stuff warms up.
Exactly. The generalized second law of thermodynamics demands that heat has to flow from the hotter object to the colder object until they reach equilibrium.
So the hot hydrogen should warm up the cold carbon. That's the forward arrow of time in action, driving the system toward higher entropy.
Right, that's what you'd expect to see.
But the researchers didn't just leave them in a standard state. They introduced something called quantum correlations.
Yes. They linked the properties of these particles in a way that just isn't possible for larger everyday objects.
And when they hit start, the heat spontaneously flowed backward. I mean, the cold carbon actually gave its heat to the hot hydrogen.
It did.
The cold got colder and the hot got hotter. In that localized space, the arrow of time literally reversed. But how? Because to me, that sounds like it just shatters the fundamental laws of physics.
Well, it doesn't break the laws of physics, but it definitely forces us to expand them. To understand how the heat flows backward, you really have to look at what those quantum correlations represent.
Okay, lay it on me.
Physicist David Jennings describes this internal quantum order as a form of fuel. So think of it like an incredibly organized library.
Okay, an organized library.
In a normal, disorganized system, finding two specific books requires this chaotic, energy-consuming search. That's normal entropy. But if you have a perfectly correlated index, you completely bypass the chaos.
Oh, I see.
The chloroform system essentially consumes the mutual information shared between the particles to drive that heat flow in reverse.
So the correlation itself is acting as a thermodynamic resource. As the heat flows unnaturally from cold to hot, that delicate shared information degrades. So the system is basically paying a massive informational penalty to force the thermodynamic arrow to point backward.
That is the exact mechanism.
Yeah.
The overall entropy of the universe is still technically increasing because those correlations are being destroyed.
But the localized arrow of time, like the heat transfer itself, reverses?
Yes. It proves that the arrow of time is not this absolute universal mandate. It's a relative concept.
That is wild.
You can literally have a quantum system where the arrow of time points backward, sitting right in the middle of a laboratory where the arrow of time is pointing forward.
Okay, I feel like I need to ask the obvious, totally selfish question here.
Let me guess.
If I leave my lukewarm cup of coffee on the kitchen counter,
Oh, I knew it.
is there any chance it could suddenly leverage some hidden quantum correlations, draw heat from the chilly room, and just boil itself?
Well, no, your coffee is perfectly safe from spontaneous boiling. Macroscopic objects suffer from something called decoherence. A cup of coffee is made of trillions of particles constantly colliding with the air, the cup, and each other.
It's too messy.
Exactly. Those delicate quantum correlations, that fuel we talked about, get scrambled and destroyed almost instantly in a noisy environment. The backward flow of time is incredibly fragile. Right now, it's only sustainable at the quantum scale.
It's like discovering a river that flows upstream, but only if the water molecules agree to share a perfectly kept secret without ever letting the riverbank know.
That's a highly poetic, but actually very accurate way to put it.
And it's not just, isolated laboratory tricks with chloroform. We also have supporting evidence from that study out of the University of Surrey.
Right, the one that looked at open quantum systems.
Yeah, let's get into that, because open systems are notoriously difficult to model mathematically, right?
Extremely, because they are constantly interacting with a vast, dissipating environment. In classical physics, when a system leaks energy and information into its environment, that information is basically considered lost forever.
It just diffuses into the background?
Yeah, this memory loss is usually what forces the one-way street of time. Like once the heat leaves your coffee, it dissipates into the room, and you can never perfectly reconstruct it.
But when the Surrey researchers modeled these open quantum systems, they found something weird. The mathematical equations describing the system behaved perfectly identically forward and backward.
Despite the interaction with the environment.
Right, despite the leaking. Let's unpack the math behind that. The source mentions something called a memory kernel. What exactly is that doing?
So a memory kernel is a mathematical function that tracks how a system retains information about its own past states. In an open macroscopic system, the dynamics are usually what we call Markovian.
And meaning the system has no memory.
Exactly. Its future state depends only on its present state, not on how it got there. The past is basically wiped out by chaos.
Okay.
But in the quantum realm, the researchers found that this memory kernel is completely symmetrical in time.
And it maintains that symmetry through what they called an unusual time discontinuous factor, which sounds like sci-fi jargon, but what is it really?
It's basically a mathematically abrupt mechanism that preserves the exact history of the quantum states. Think of it like dropping a pebble into a pond.
Okay, I dropped the pebble.
Usually the ripples hit the shore, they bounce back chaotically, and the original shape of the splash is just lost forever.
Right, it's just turbulent water.
But the time discontinuous factor in these equations acts as an absolute mathematical guarantee that the precise information of the splash is preserved in the ripples.
No matter how much they interact with the muddy shore.
Precisely. Because that information is mathematically preserved, the equations maintain perfect time reversal symmetry. The tape can run backward.
This brings up a massive, psychological hurdle for us, I think. We were looking at a paper earlier regarding change blindness.
Oh, yes, the psychological phenomenon.
Right, where our brains are wired to filter out information we don't expect to see. Like, if you aren't actively looking for a gorilla walking through a basketball game.
Your brain simply won't register it. It edits it out.
Exactly. I really think we suffer from chronological change blindness. We are so biologically hardwired by the decay of our own bodies to expect time to be a one-way street. We literally struggle to even process the reality that physical equations work perfectly in reverse.
It's a very apt comparison. Our biological interface with reality absolutely demands a linear narrative to function.
We need a past, present, and future just to get out of bed in the morning.
We do. But when the foundations of quantum mechanics show us that the arrow of time can point backward, and the foundational equations don't care about past or future, it totally shatters that linear narrative.
It really does.
If the past can mathematically be undone, or if the future is just as mathematically valid as the past, it forces us to ask a terrifying question. What exactly is real?
Which drops us directly into a classic metaphysical battleground. When we look at the philosophy of time and the sources, there are traditionally two heavyweights in the ring.
In one corner, you have presentism.
Right. This is the intuitive idea that only the now is real. The past is dead and gone. The future doesn't exist yet. It is only the razor's edge of the present moment.
Yeah. And in the opposing corner, you have the block universe, often referred to as eternalism.
Which is heavily inspired by classical relativity.
Yes, it argues that the past, present, and future all exist equally in a frozen four-dimensional block of spacetime.
So under this framework, my birth, the moment you are currently listening to this deep dive, and my eventual death are all just like equally real coordinates.
Yes, time doesn't flow at all. It just statically is.
That concept totally drives some physicists crazy. We actually have this fantastic quote from physicist Avshalom Alitzer, who violently rejects the block universe.
He does not hold back.
No, he doesn't. At a cosmology conference, he literally stated, and I quote, "I'm sick and tired of this block universe. I don't think that next Thursday has the same footing as this Thursday. The future does not exist. It does not. Ontologically, it's not there."
You can really hear the visceral frustration in his words.
Yeah, he was heated.
And his frustration is completely justified, particularly when we try to reconcile the block universe with quantum mechanics. But strict presentism has massive theoretical flaws as well.
Like what?
Well, if the past truly isn't real in any sense, how do we explain causation? How can something that is essentially nothing exert a physical influence on the present moment? Both frameworks fail to fully explain the reality we actually observe.
Enter Tenzin trap.
Yeah.
And a 21st century philosophical framework called existential realism.
This is the paradigm shift that our sources suggest finally bridges the gap.
Tripp solves the dilemma by completely separating two concepts that we normally just use interchangeably in everyday language: existence and reality.
The precision of those definitions is really what makes the framework so powerful.
Okay, break it down for us.
Under existential realism, the concept of existence is strictly limited to the present moment. To exist means to be materially, empirically accessible right now.
It requires concrete, measurable presence.
Exactly. But reality is a much, much broader category. Reality encompasses the entire vast, causal, and informational web of the universe.
So, under this framework, everything that exists is real, but not everything that is real exists.
Let's ground that with a concrete example. Think of a dinosaur fossil, or the ruins of Pompeii.
Right.
The actual flesh and blood dinosaur does not exist anymore.
Right.
Its material presence in the now is completely gone.
Right. A strict presentist would say the dinosaur is literally nothing.
But existential realism argues that the dinosaur is fundamentally real because it belonged to the causal fabric of the world. It left enduring traces, fossils, evolutionary impacts, carbon footprints in the present.
So the past is ontologically real even without current material existence. I really love this way of looking at it. I kind of think of it like a financial ledger. The past entries in the ledger are permanently recorded in ink. They dictate your current account balance, so they are incredibly real, but they aren't the active live transaction happening right this second.
That's a great analogy.
But what about the future, though? How does existential realism handle next Thursday?
Well, the future doesn't exist either, because it has no material presence. But it can be real as a structured possibility.
Like a prediction.
Exactly. Consider a predicted solar eclipse happening next year. It has no material existence today, but it is real as a highly probable outcome grounded in current orbital mechanics.
It's real enough that scientists are currently building telescopes and planning schedules around it.
Right. The future is real as a potential that exerts anticipatory influence on the present.
So existence is the active transaction happening right now, but reality is the massive ledger encompassing the causal past and the structured probabilities of the future.
You've got it.
That doesn't just feel like a clever linguistic trick for armchair philosophers. It feels like the exact ontological blueprint we need to explain the most baffling quantum experiments ever conducted.
It absolutely is the blueprint we need. Let's look at the notorious measurement problem in quantum mechanics.
Oh, this is where it all comes together.
Before a quantum system is measured, it exists as a wave function. Basically, a superposition of many possible states.
Yeah.
It's totally indeterminate.
Right, an electron could be spinning up or spinning down, and until a scientist actually checks the instrument, the math literally says it is doing both simultaneously.
Yes. Now, if the block universe were true, and everything in spacetime was already pre-written and frozen, a truly probabilistic wave function makes absolutely no sense.
Because the final outcome would already be a fixed fact sitting at some coordinate next Thursday.
Exactly why the block universe fails at the quantum level. But existential realism explains the wave function perfectly. Before measurement, those various possible outcomes of the electron are real. We know they are real because they exert actual physical influence.
Like creating interference patterns that we can observe.
Exactly. But they do not exist as definite classical facts.
So under this model, the present moment, the now, is specifically defined as the exact transitional edge where mere reality, that floating cloud of mathematical possibility, collapses into existence as a concrete fact.
The now is the site of becoming. It's the single active point in the universe where the indeterminate future is forced to make a choice and become the fixed, causal past.
I want to test this framework against one of the wildest experiments in all of physics, John Wheeler's delayed choice experiment.
Oh, this is a mind bender.
For you listening, the setup of this experiment is just wild. Imagine shooting a single photon of light into an interferometer. It's basically a maze with a beam splitter. At the first splitter, the photon can take path A, path B, or because it's quantum, it can act like a wave and take both paths simultaneously.
And the crucial part of Wheeler's setup is the delay. We don't decide how to measure the photon until after it has already passed that first beam splitter.
Right. If we insert a second beam splitter at the end of the maze, the photon acts like a wave that took both paths. If we leave the second splitter out and just put detectors at the ends of path A and path B, the photon acts like a particle that only took one path.
But we make that choice after the photon has supposedly already made its journey.
Yes. It looks exactly like a choice we make in the present, reaches back in time, and retroactively determines whether that photon acted like a wave or a particle in the past. Like, are you telling me I can rewrite reality?
It looks exactly like retrocausality, which is why it breaks so many classical models. But let's apply existential realism here.
Okay.
There is no magical backward time travel happening here. The photon's past state wasn't a fixed existent fact that got changed by your later measurement.
Wait, so what was it?
While it was moving through the maze, its path was merely a real but completely undetermined potential.
So it was just a blank entry in the ledger. It was part of reality, but it hadn't dropped into existence yet.
Precisely. The past, in that specific quantum state, was left entirely open. Your delayed measurement in the present doesn't change the past. It finalizes it.
Oh, wow.
As John Wheeler himself argued, the past has no existence except as it is recorded in the present. Until you make that measurement, the reality of the photon's path is just a set of hovering possibilities.
And your measurement causes that reality to finally collapse into existence, writing the entry into the ledger for the very first time.
Exactly.
That fundamentally changes our relationship to our own lives and the universe. I mean, we are not watching a static, pre-recorded movie play out on a screen where all our choices were baked into a 4D block at the dawn of time.
No, we are the live performance. The universe is actively being written at the exact boundary of the now.
It restores a profound sense of agency that classical physics often just strips away.
It does. The future is not an existent destination you are helplessly hurtling toward. It's a set of real possibilities that you, as an observer and participant, are actively collapsing into existence through your interactions in the present.
So let's bring this all together for you, listening right now. We started by stripping away the illusion of the majestic river of time. Time is not a fundamental container you are moving through.
It is merely the localized measurement of change, of entropy, of the physical world breaking down.
Right. And we saw that at the quantum level, where we can manipulate that entropy, the arrow of time isn't absolute. By utilizing quantum correlations as fuel, that arrow can be made relative and can even run backward mathematically and thermodynamically.
And most importantly, why should you care about a philosophical framework like existential realism? Because it frees you. You are not trapped in a deterministic block universe.
You stand right now listening to this deep dive on the razor's edge of the present. It is the only place in the cosmos where existence happens.
It's the specific point where your actions and observations collapse infinite, hovering real possibilities into concrete, unchangeable facts.
But if we accept this, if we accept that time is not an independent dimension, but merely an emergent property of change, causality, and entropy, it leaves us with one final, kind of haunting question about the cosmos.
You're talking about the end of the universe.
The heat death.
Yes. In the cosmological scenario of universal heat death, all entropy reaches its absolute maximum. Energy is perfectly evenly distributed across the void.
The stars burn out, the black holes evaporate.
Eventually, even quantum fluctuations cease. There is no more heat flow. There is no more change, no more transitions from possibility to actuality.
If time is strictly the measurement of change, what happens when change stops?
Does time itself literally dissolve? Does the universe just turn time off, leaving behind a silent, timeless eternity?
That is a staggering thought. If the biological machine finally stops breaking down and the glass shatters into dust that eventually stops moving completely, the clock doesn't just stop ticking. The very concept of the clock ceases to exist. We'll leave you to mull that over. Thank you for joining us on this deep dive into the source material. We'll see you next time, right here.